Okay, welcome to week 8 tutorial session. So I'll just start the session now and I'll discuss the problems. Okay, so uh, welcome to week 8 tutorial session. So in this week we will be discussing on different ways to score the motives. Okay, so we are given a bunch of these motives. These are like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we are having 10 motifs, and each motif is having a length of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so we are having these 10 motifs. Each motif is having a length of 12. Okay, so now we will be looking into different methods to score these motifs, scoring of motives. Okay, to score these motives, so first of all, more likely it is, these are different ways to like rank or give a scoring on these motives, or to give like a ranking on these motives and how good these motives are, and how like what is the like what kind of motives are these, and to understand these motives. Okay, so first of all, we'll begin with what is called as the consensus of the motives. This is more like a reference genome that you saw in week 6. It is kind of like what is most likely to be the actual motif, but there are some mutations in some of these motifs. So what motif is actual likely to be the what motif is likely to be the actual motif, but these are some variations of the motifs given here. So for consensus of motifs, to compute the consensus of motifs, what we will do is at every position of the motifs, we will find the nucleotide which occurs the most. Like for example, in the position number 1, we can see that T is occurring 1, 2, 3, 4, 5, 6, 7 times. Okay, and A is occurring like, okay, let's just go to count of motifs and then we'll compare. Okay, so what count of motifs does is, this is a way to rank the motifs. So what we are going to do is, in count of motifs, we will be counting what is the number of occurrence of a nucleotide at each position. Okay, what is the, I'll repeat again, what is the number of occurrence of every nucleotide at each position. So like now here we are having 1, 3, 4, 5, 6, 7, 8, 9, and 10. Right? So we are having 10 motifs. So what I'm going to do is, at the position number 1, okay, so this is position number 1. At the position number 1, I am going to count how many are the, what is the number of occurrences of A, C, G, and T. Okay, so let's begin with A. So if you can see here that A is occurring exactly twice. This is one time, and this is 2 times. Okay, so A is occurring at the 3rd position once and at the 5th position once. So A is occurring 2 times in at the position number 1. Okay, so uh, okay, so A is occurring at the position number 2 times. So that is why what we are going to do is, the number of the count of the nucleotide A at the position 1 is 2. Okay, so that is what we will be doing here. We will, at the position number 1, for the value for the nucleotide A, we will have the value 2. Okay, similarly for C, if we look into the position number 1, we can see that C is occurring exactly once in this position. So we have 1 at this position, and G is occurring 0 times. There are no G's at the position number 1, so this means that G will be occurring 0 times. Okay, and T is occurring 7 times. We have already counted that. So 1, 2, 3, 4, 5, 6, 7. Okay, so T is occurring 7 times. Similarly, at the position number 2, we have that C is occurring 3 times. Sorry, 1, 2, 3, 4, 5, 6 times. So C is occurring 6 times. Now T is occurring 2 times. So T is 2. A is occurring 2 times. So A is 2. And G is not occurring at all. So G is 0. Okay, so this is how we compute count of motifs for every column, basically at every particular position across all these motifs. What is the number of occurrence of each of the different nucleotides that we have to just count. Okay, so this is what count of motifs is. We just have to count these the number of occurrences of each of these nucleotides. Okay, so now once this count is done, we were going to look into something what is called as a probability kind of a structure. In count, we are just actually counting these values, but we want to represent it as a probability. Okay, so what we will do is the probability of occurrence of A at the position number 1 is what? So there are 10 motifs, right? So there are 10 motifs. Out of these 10, there can be 10 nucleotides at the first position, at this first position, because there are 10 motifs. At the position number 1, we can have 10 nucleotides, right? So out of them, 2 of them is A. So what is the probability of occurrence of A at the first position? It is obviously 2 over 10, right? Which is basically 0.2. Similarly, for C, C is occurring once at the position number 1. So that means there are out of 10 motifs, out of 10 different values that can be there, C is occurring exactly one time. Okay, so what we will do is the probability of occurrence of C at the position number 1 will be equal to, so there are 10 motifs here. So basically there are 10 different nucleotides at the position number 1. So what is the probability of occurrence? C is occurring once, okay, out of these 10 different values that is possible, C is occurring exactly once. So what is the probability of occurrence of C at the position number 1? Okay, so that is obviously C is occurring once out of 10 times. So that is why we have 1 over 10, which is equal to 0.1. Okay, so at T is occurring 7 times, right? So at the position number 1, out of 10, T is occurring 7 times. So the probability of occurrence of T at the position number 1 is 7 out of 10, which is equal to 0.7. Okay, so basically what I'm trying to say is, if in the count motifs once you compute the count motifs, if you instead of the exact number of times the nucleotide is occurring, we have another way of representing the probability of occurrence of that nucleotide at that particular position. The table that we get, that is called as profile of motifs. Okay, so here what we do is, instead of the number of occurrences of the particular nucleotide, we just represent the probability of occurrence of that particular nucleotide at that particular position. Okay, so here count was 2, there were 10 motifs. So the probability of occurrence of A at position number 1 is 2 over 10, which is 0.2. So in profile of motifs, we will have the value 0.2 for the nucleotide A at the position number 1. Okay, we can just do that, repeat similarly for every other value. Okay, now let's go to what is called as consensus of motif. Consensus of motif is basically the motif, the nucleotide at every position, what nucleotide occurs more frequently, the most number of times. So in the first position, we have T is occurring 7 times, okay, A is occurring twice, and C is occurring once. Okay, C is occurring once, A is occurring twice. So obviously, which nucleotide, and G is not occurring at all. So which nucleotide is occurring the most number of times? It is T. So that is why we have T at the first position. Then similarly, at the second position, we have C is occurring 1, 2, 3, 4, 5, 6 times. T is occurring 2 times, and A is occurring 2 times. So obviously the maximum number of times, the nucleotide which is occurring the maximum number of times is C. So that's why we have C at the second position. Okay. Similarly, at the third position, we only have G. There are no other nucleotides. So that's why we have G at the third position, and so on. Okay. So whatever motif you get, so once you do this, for every position we compute the what nucleotide is occurring the maximum number of times, and then once we do this, we can combine all of this into one string. So the string that we will have here is T, C, G, 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 A, T, 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 C, C. Okay, So this particular string is called as the consensus of the motifs, okay, of this set of motifs. Okay, this sequence is called as consensus of motifs, okay, of these motifs. Okay, so now this is how we compute the consensus of motifs. Now score of motifs is basically how many mistakes have been done. You have to count how many mistakes have been done throughout in this entire set of 10 cross 12 motifs, how many places you have done a mistake. What it means is, like, at the first position, we should be having T, right? Because the consensus says T is the T should be there because T is occurring most frequently, but now we are having A and C at three different positions, right? So these three different positions do not match up with with our consensus, or doesn't match with the majority. Okay, so we are going to count these as errors. So this C and two A's. Okay, so at the position number one, this C and these two A's will be a errors, or will be the mistakes that we have done. Okay, so this is what we get here when we sum the, so these three. So for this particular column, that is the position number one, we are having three different mistakes, right? Then at the position number two, we can see that we are having two T's and two A's, which should not have been there, and majority is C. So we were expecting C at these four positions, but we are having two T's and two A's, which are basically probably these are some mistakes and while reading the motifs or something. Okay, so we are going to count all four of them also. So here 3 plus 4. Okay, 4 from the second position, 3 from the first position. Now in the third position, we are having all G's. And our consensus is also saying that G should be there because G is the majority. So that is why we are having all G's, and there are no other nucleotides present. So that means there is zero error. Okay. So that way we can count the number of the number of motifs or the number of mistakes in this entire matrix which doesn't match up with the consensus, and sum it up. The total number of this will give you the score. Okay, so we can do one thing, like for example, we take this one column, and in one column we see that we are having 70s. Let's say in the last column we are having 1 2 3 4 5 6 C's, but there are 4 T's, right? So if there are 4 T's, that means a majority is C, but then there are 4 positions which do not match up with the majority, so our mistakes are possible in these 4 different positions. So that is why we are having a 4 over here. Okay, so this is one way. We take the position of the consensus and then we count the number of motifs which do not match up with with the majority nucleotide at that particular position. Okay, there is another way out. You take this particular consensus, and then you find for every particular motif, you find which of these motifs do not, what is the Hamming distance of each of the motifs with the consensus, and then you add it up. What I mean here is, you take the consensus here and then you take the first motif. Now find the number of positions where they are differing. Okay, so T same, then C same, then we are having 4 G's, and here also I am having 4 G's, which is same. Then I was supposed to have an A, but now I am having a G. So this is a different. This is a place where it is different. Okay. Then we are having 3 T's. I was supposed to have 3 T's, and I am having 3 T's. Then I am supposed to have 2 C's, but I am having 2 T's. So there is more likely that these two are also errors. Okay. So my Hamming distance of this first motif to this consensus will basically be 3, because it is differing at these 3 different positions. Okay, so this will be 3. Similarly, I can compute the Hamming distance of the second motif with the consensus, the third motif with the consensus, and so on. And ultimately, once we sum up this Hamming distance, we will again get 30. Okay, the same score. So for computing the score, we can either take the consensus and find the Hamming distance of each motif from the consensus and then sum it up, or we can take every position of the motifs and find how many of the motifs find how many of these nucleotides or how many of these motifs do not have the majority value, and then we sum it up. Either way, we will get the same value. Okay, so this is how we compute score. So this is score is done, this is consensus. Then I have already discussed count of motifs and profile of motifs. Okay, so then we will discuss something called as column-wise motif entropy. So this is a formula. So once we have this column-wise to compute column-wise motif entropy, it is like very easy to compute this value from the profile of motifs. Okay, I should not have put this motif figure over here. I should be having the profile of motifs over here. Okay, so I'll replace it before sharing the slides. Instead of this motif blocks, I will replace it with the profile of motifs. So what we are going to do is we will use the profile of motifs to compute the column-wise motif entropy. So this is the formula. So like what we are going to do is, let's say we want to compute the profile, sorry, not the profile, the column motif entropy. We want to compute entropy at the first position. Okay, so if we want to compute the entropy at the first position, what we are going to do is each of these values will be our PIs. So what we will do is PA times log of PA. Basically, what it means is the probability of occurrence of the nucleotide A at the position 1. Here I am computing the entropy for column number 1. Okay, entropy for column number 1. Okay, so to compute the entropy for column number 1, what I am going to do is, sorry, this is negative. So I will take the probabilities of each of these nucleotides and I will find compute probability of that nucleotide at that position or at that column or at that position times logarithm of the same probability. Okay, and then we will sum it up. So this is basically negative of probability of A times logarithm of the probability of A at the position number 1 plus probability of C at position number 1 logarithm of probability of C at position number 1 plus probability of G at position number 1 times logarithm of probability of G at position number 1. Okay, and this will again be probability of T times logarithm of probability of T. Okay, so now we are already having this 0.2 value as the probability of A. We have already computed profile of matrix motifs. So we'll just use the same value. So this will basically be equal to probability of A at position number 1 is 0.2. So we have 0.2 times logarithm of 0.2 plus, sorry, this is minus. We have negative over here. So I'll just put minus. Okay, minus probability of C at position number 1 is 0.1. So we have 0.1 times logarithm of 0.1 minus 0 times logarithm of 0. Okay, because probability of G at position number 1 is 0. We have 0 times logarithm of 0. Then we have minus probability of T is 0.7 at position number 1. So we have 0.7 times log of 0.7. Okay, so now this will be, okay, so for this particular case, logarithm of 0 as we know is minus infinity. So we are not going to consider it as minus infinity or anything, but because it is 0 times minus infinity, we are going to consider this as 0. Okay, so now this value will be equal to 0. These values we can count it 0.2 times log 0.2 plus 0.1 times log 0.1 plus 0.7 times log 0.7, and whatever will be the value, that will be the entropy of that first position. That will be the entropy at the position number 1 of the motifs. Okay, so this will be negative of this sum. Okay, remember the minus sign. So okay, so this is called as the entropy for column number 1 of entropy for position number 1. The second important thing to note here is this is logarithm to the base 2. Please don't confuse it with other bases. Okay, so we'll be computing it as logarithm to the base 2. So now once this column wise motif entropy is computed, we are going to, this is something, there is something called as motif logo, which is basically a representation of the motifs in a pictorial format. Okay, so what we are going to do is we'll use this motif entropy, and then for every particular nucleotide we are going to compute this value pi log pi. Okay, so this is column wise motif entropy, that is one thing is done. Okay, then there is something called as this motif logo. This is a different thing. Okay, so there is something called as motif logo, which is basically for every nucleotide we compute this value pi times log of pi. Okay, and we plot it negative negative of this. Okay, negative of pi times log of pi. We compute this particular value and we plot it according to the position, according to this particular value, whatever the value will come. So what it means is at the first position, let's say p of c times log of pc, whatever will be the value, that will be the height of the c nucleotide at the first position. Then we have pa times log of pa. Tamanna, can you please mute? There's a little bit of noise happening. Okay, thanks. So for PA, we will then have PA times log of PA, because count probability of C was less than probability of A less than probability of B. We already know that. Okay, from the profile matrix, we already know these values. Okay, so now PC times log of PC will be less than PA times log of PA, and this will be less than PT times log of PT. I don't know the exact values. That's why I'm just assuming, I'm just believing this will be true, because from the profile of motifs, I believe that will be true. Okay. You can compute that, these values. This will be not, this is not PA times logarithm of PA. This is negative of PA times logarithm of PA. This values will be smaller accordingly, because the probability values are smaller. I don't know the exact values. You can count it up. Okay, you can count the values. So now see, we have PC times we count, we compute minus negative of PC log PC, and whatever will be the value, we will be, that will be the height of C at the position number 1. Then we have negative of PA times log of PA. So whatever will be the value from the height of PC, we will plot that to the next height. Okay, so we have C over here. Let's say PC is coming to this particular position. C is coming to this PC log PC, or the entropy for the nucleotide C. Okay, negative of PC log PC is coming to this particular position. Okay, so then what will happen is we will compute negative of PA log PA. So that will be over this, from this particular position to whatever position it will go. Okay, so this to this is PC times log negative of PC times log PC. Okay, and okay, PC times logarithm of PC. Now A, suppose whatever is PA times, we will compute negative of PA times minus PA log PA, and whatever will be the value, will take that particular value from this position. So this to this will be PA times negative of PA times log PA. Okay, so this will be our A. So our A will be placed on this C. Okay. Then similarly for T, we will compute minus of PT times log PT. So whatever the value will come, we will plot it from this point to the top. Okay, and whatever will be the value, until that our T will be represented. Okay, so as you can see, this is kind of, we are just kind of adding up these values. Okay, these values we are adding up. See, we are having PC log PC first, then we are adding up PA log P, negative of PA log PA, then we are adding up negative of PT log PT. So this is kind of, we are keeping on adding up these values. Okay, so when we are adding these values, what do we get from the formula? As we already discussed, we will get the motif entropy at that particular position. Okay, so here in this motif logo, the total height or the maximum height of that particular of the nucleotides at a position gives us the motif entropy. Okay, so now uh, this the maximum value possible if we do these logarithm summations and all of this, the maximum value possible for a motif entropy at a particular position is called as the is 2. Okay, the maximum value possible at a position will be the for the motif entropy is 2. Okay, so this particular value 2 minus whatever the motif entropy we get, that is called as the information content. Okay, 2 minus this particular value is giving us the information content. Okay, so this is how we compute motif logo and the motif entropy. So it's not, it won't be a big of a headache to compute this. But from this particular chapter, these are the major topics that we should be looking into. You should be looking into. I think there are 2 questions from motif logo in the assignment. We are trying to constraint this motif logo thing, because it will be a lot of confusion to constraint questions from motif logo, because it will be a lot of confusion on what the values are and everything. So that's why we are trying to limit the questions from motif logo. But from motif entropy and from the other motif scoring methods, you can expect some questions. Okay, you can expect a lot of questions. But there isn't much to play around with in this chapter. So what you can look into is for the additional questions or something, what you can do is you can just look into different methods on how to compute these values from each other. Like, how do you compute the score given the motifs and the consensus? How we know how to compute the score, right? Given the motifs and the score, we know how to compute the consensus. But the question is, given count of motifs, how do we compute the score? Okay, that can be a question. From the count of motifs, how do we compute consensus? Similarly, from profile of motifs, how do we compute count of motifs? We know how to compute profile of motifs from count of motifs. But what about the reverse one? From given the profile, can we compute the count of motifs? Similarly, given the profile, can we compute the consensus? Given the profile, can we compute the score? Okay. Similarly, from the count to entropy, can we compute the entropy of each of the positions or each of the positions of the motifs from the count of motifs? I already discussed from the profile of motifs. What should be the formula for given the count of motifs? If we are having the count of motifs, what should be the, how do we compute the entropy at a particular position? Okay, so these kind of interchange of questions you can expect. There aren't much. From then after this, we are having 3 different algorithms, which is basically the median algorithm. I'm not able to recall the name right away, but it's something in median algorithm. Then there is the greedy algorithm. We have a Gibbs sampling algorithm, and we have a randomized motif search algorithm. So from the 3 algorithms, I would suggest you to understand how the algorithms work, but don't no need to go deeper into that, because it will be more or less MCQ. It will be MCQ questions and everything. So you should be looking into the pseudocodes of those 3 algorithms. Look into the pseudocodes, and you should try to understand the difference between these algorithms. Okay, so try to see the difference between these algorithms. Try to understand the pseudocode for these algorithms, and try to understand what is happening in these 3 algorithms. Not about the median finding algorithm, but from the last 3 algorithms. The greedy algorithm, the randomized motif search, and the Gibbs sampling. Try to look into the difference between these 3 algorithms, and what are the how these algorithms work, and the pseudocodes of them. Okay, so that's all from this particular chapter. There isn't much, only it's kind of an easy chapter. So there isn't much from this. So this is from week 8 content. Okay. Any doubts or questions or anything?
Good evening, ma'am.
Yes.
Ma'am, I just wanted to know, like, when we are doing that suffix try and suffix tree, so we have to like count the length as like 0, 1, 2, 3, 4, or like 1, 2, 3, 4, 5. Like if A,
For
B,
week,
C, D, E is
yeah,
there.
for week 6 content, the suffix tree, suffix try chapter, the length will be computed from 0 onwards.
Okay, ma'am. And dollar would be included, right?
Yes, unless mentioned, please assume dollar is always included.
Okay, 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 ma'am. Thank you.
Okay. So the questions that we were discussing last time, were you able to solve it, or do you
Um,
have any questions?
Ma'am, I did that at my own only. I couldn't join the session.
No, that's fine. What I'm
But
asking
ma'am,
is
there
that,
was a question in the graded assignments in the end. So that question was coming like if I was doing A, B, C, D dollar, including, they were saying that including dollar, it is of length 5.
yeah.
So, but we are taking index as 0, right? Not length. Length would be like 1, 2, 3, 4, 5 only. My doubt is
Yeah.
like I couldn't ask properly, but yeah, that is the thing. Like index is 0, 1, 2, 3, right?
Okay, we will discuss that. There is one important thing that I missed from week 8. Let me just discuss
Okay,
that
okay.
and we'll come back to that. Okay? So there is something called as profile most probable gamer. Okay. So I forgot this part. This is most one of the most important topics in this particular chapter, because this is something that is used to compute the to in the Gibbs sampling and the randomized multiple search algorithm. Okay. So suppose we are given this schema. There is a long gene. Okay, there is a long genome sequence or a long gene sequence or something, and there is a KMA. Okay, you are given this KMA. Let's take this particular KMA. Okay, so what we want to find is the and the profile of the motifs. Okay, you know the profile. Okay, what you want to compute is the probability of this particular uh, the probability of occurrence of this particular KMA in the motif set. Okay, the probability of occurrence of this particular KMA in the motif set. So how do we compute that? We take the profile of the motifs, and for every nucleotide at every position, let's just mark it. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay. So at the first position, we have the nucleotide A. So we go to the nucleotide A at the position number 1, 5, 6, 7, 8, 9, 10, 11, 12. Okay. At the position number 1, A has a probability of occurrence is 0.2. Okay. So now we are having A at the first position. So I'm going to take 0.2. Okay. Then what is the probability of occurrence of C? So the second position in this particular case, we have C. So I'm going to the profile matrix and I'll find what is the probability of occurrence of C at the position number 2. Okay. So the probability of occurrence, so we go to the position number 2, the nucleotide C, and we see that the probability of occurrence of C at position 2 is 0.6. So we multiply this 0.2 with 0.6. Okay. Then we have G. What is the probability of occurrence of G at the third position? So the third position G has a probability of 1. So we multiply 1. Okay. And we repeat this for every one of these nucleotides in the KMA, every one of those positions. We are having 12 values, 12 nucleotides. The length of the KMA is 12. Length of the motifs is 12. So that's why we will be having 12 different values. We should multiply for every one of these nucleotides at every each of these positions. We take its probability of occurrence of that nucleotide at that position, and we multiply it. Okay. So once we do this, whatever will be the final value, that is the probability of occurrence of this particular KMA as a motif. Probability that this particular KMA is the consensus, or probability of occurrence of this particular KMA in the list of motifs. Okay. So now suppose we are given a sequence of a genome sequence of length n. We can what the profile most probable KMA means is what is the KMA which has the highest probability with respect to this profile matrix. Okay, so given this profile matrix, what is the KMA which has the highest probability, or the KMA, the highest probable KMA? Okay, so when we are given a genome sequence, what we are going to do is to compute to find the profile most probable KMA. We will find every possible KMA in this particular genome sequence. Okay, so there will be n minus k plus 1 KMAs. Okay, for each of these n minus k plus 1 KMAs, We will compute this probability value, and whatever came out, for whatever came out, we are getting the highest value. That particular k-mer, let's say this is the highest possible value in this genome sequence. Okay, out of all the k-mers, this is the highest value. This means that this k-mer, ACGGGGATTACC, okay, this particular k-mer is the profile most probable k-mer. Okay, so this is the concept of profile most probable k-mer, and this is used extensively in Gibbs sampling, for Gibbs sampling and randomized motif search. Okay, so that's it from this week's content. Okay, so we will discuss the doubts from week 8's content. We will discuss the doubts from week 6 content now. Remember, you were asking something.
Yeah, ma'am. It was like if we are doing ABCD dollar, so it would be of
Okay,
length 5. It is length 5, right?
ABCD dollar has a length 5.
It
Okay,
has. Okay. I was doing ABCDE dollar. That's why I was confused. So it is like we are
okay.
counting it as like 0, 1, 2, 3, 4, 5 only, right? Including dollar.
This is, yes. No, 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 no.
Hmm.
Okay, let's take a particular genome sequence. Okay, ACGTA dot. Okay, this is a sequence. Okay,
Okay, ma'am.
so the indices will go from 0, 1, 2, 3, 4, 5. Okay,
Yeah.
but
Hmm.
length of this is equal
6.
to 6. Okay, the
Okay.
number of characters, or number of characters in this particular
Yeah,
sequence.
yeah, ma'am. Okay, okay. Thank you. Thank you so much.
Yeah. Any doubts from week 6, week 8, week 5, or week 4, 3, 2? Any doubts? I am not going to discuss doubts from week 7, but any other weeks you have any doubts?
Just one question. I was going through some previous year questions, just generally asking. More all questions are focused from week 5 to 8 only. There's nothing from week 1 to 4. So,
For
just
week
want to
2,
understand. Say that
sorry,
again.
quiz 2. For quiz 2,
Yes. Yes.
quiz 2 syllabus is week 5 to week 8.
Okay. Great. Great. Thank you.
Whenever, whatever will be the syllabus, we are equally distributing the marks. Okay? Or some weeks will be completely ignored for enter, or it will be equally distributed among the weeks.
Understood.
Okay, any other questions or anything? Okay, if there are no questions, then we'll end the meeting then. Were you able to solve the questions last time that we discussed, or do you want?
I I had tried
Sorry,
one question where so I had solved it, but I cannot
okay,
remember the question, unfortunately. So you had given two
that's
questions.
fine.
I was able to solve one of them.
Okay, that's great. Even one is.
It was, I think, you had, yeah, I was able to do one.
Yeah, that's fine. No, no issues. It's good actually.
Okay.
One is good. They were hard questions to do. Okay, so yeah. Anything else? You want to discuss the second question, or do you want to try it more?
No, I'm going to try it some more. So I'm
Sure.
actually started my revision, so I'm going to go over it once. If I can't do that, I'll post it on Discourse like you had mentioned.
Yeah, definitely. Actually, with discourse, I rarely look into discourse. If you want immediate answers, I'm just letting you know this. If you want like immediate right away, anything emergency, it's not that I'll not reply on discourse. I will, but if you like want right away, you want the solution or want anything, then just ping me or tag me on the Google chat. Okay.
Okay. Now, usually you respond much faster than other instructors. So I
Okay.
see your response in a day at least. So that's good enough. But otherwise, normally we post in GChat. I'll do that, like what you're suggesting.
Yeah, actually with GChat, it's the notifications come on my phone, so I just look in my phone and I just respond it right away. If it is possible
Okay.
to solve it right away. But with this course, I have to like switch on my laptop and everything, so it takes time. Sometimes I do that once or twice in a day. So that's
Understood. Understood.
Ma'am, where can we see that questions
Which questions?
that you are talking about?
It's
They
in the
are
live
in the
session.
the live session. So from the live session last week, we had discussed two additional kind of questions. There were two additional questions that I had posed, and you guys had you wanted to solve it on your own. So they are on the tutorial slides itself. You can find the questions in the tutorial slides, or you
Okay,
can look
okay, ma'am.
into the live session for last week, and you'll find the questions. I don't remember the questions right away, but you can
Okay,
look into
ma'am.
the tutorial slides of the live session. Okay.
Okay, ma'am. Thank you.
Okay, I'm going to stop the streaming then. End the session. Okay. Okay, you guys don't have any